All right, so this is the final kind of topic we're going to be going over, which is regression, simple linear regression, and then multiple linear regression. Um, if you're interested in this stuff, the next course in the sequence, so E371 is econometrics. We dive deeper into these issues. So if you find it interesting, this is a prerequisite for that class. Um, that being said, let's go here. And I'm going to switch the video so you can kind of see any work that I'm going to do over here. So regression analysis, we've already talked, just to relate to some things we've already talked about. We've done hypothesis testing for unknown population means and unknown population proportions. We can also do hypothesis testing for different statistics that we've talked about, like the correlation coefficient or the covariance. So remember, with these two measures, what we were trying to do was pick up on what the relationship was between two variables. So, variable X and variable Y, are they positively correlated, negatively correlated, or is there no relationship? Is that covariance or is that correlation coefficient equal to zero? So we're going to take it a step further, right? And then calculating just having these measures of how two variables are related. And what we're going to think about is what we're going to do is called estimating a regression equation. So we've got two different variables, X and Y. I might think that Y depends on X or is some function of X, right? So here I'm writing my dependent variable Y as a function of my independent variable X. So X is going to change, and then as a result, Y will change. Okay. So here, this slope of B, right? So just we'll go here. If I'm thinking about what I'm, oh, switch this around. If I think about what I'm doing, right? This is just kind of the general form of an equation, right? So as X changes, right? Let's say X was 3, I could plug a 3 in here. Whatever my slope is and whatever my intercept are, I could then determine the value of Y. So really all we're doing with this regression equation is saying, here's all these different values for X. It's going to start, right? Even when X is equal to 0. So if X was 0 here, the only thing we're left with is the intercept. Right? And then as X goes up, if B is positive, right, our slope is positive, we're going to have kind of this line that essentially for different values of X, I can tell you the different predicted, we'll kind of write our predictions with a hat, the different predicted values of Y would be on this line. Okay. So conceptually, this is we're trying to figure out, given these two variables, what does the relationship look like between them? How much does Y go up by as X goes up? Or how much does Y, if we had another example, maybe it starts here and decreases. Right? So that's what we're trying to do. But how can we use data to figure out this relationship? So, just in terms, I've already mentioned some of them before we get too into the weeds here. Our Y variable is the one that we think depends on our other variable X, right? So we're going to call it our dependent variable or our Y variable. Our X variable on the right-hand side is our independent variable. It changes in that variable X is what then causes changes in variable Y. So regression analysis is going to be the statistical technique. We look at all the observed data to be able to pick up this relationship between our dependent and independent variable. And we can actually do variables, which I won't start out with, but we'll eventually get there. So, maybe I had a data set, and if I had every single observation, I plotted it. So let's say we go all the way back to like beginning of the class, we're doing a scatter plot. Well, you can kind of imagine if I could draw a line that kind of best fits this data, right? So you can kind of see here, okay, when X values are higher, these Y values tend to be a little bit lower. When X values are lower, Y values tend to be a little bit higher. If I had to draw a line that kind of best fit this data, which you probably have talked about lines of best fit in like science, high school science and things like that, um, then really what I'm trying to do is say, okay, based off the data, if I were to be able to draw a line that best fit this relationship, where would its intercept be? And what would the slope be? Okay. So we're thinking about, we have multiple types of it. Like maybe I have something that looks like this. So if I drew a line of best fit through this data, I don't know, it's kind of flat. That would be no relationship, right? And this one here, it looks like it's positive when X is higher, Y tends to be higher. Negative, we kind of already looked at this at the setup. So all I'm trying to figure out is what's the slope of this line of best fit, right? What is the value of, I'll go back here. What is the value of B, right? So I'm not going to go through these quick because we're not going to dive into nonlinear issues, but we're going to keep everything linear. The next level would be you can actually look at nonlinear relationships, right? And so there you have like a squared term. So it could be concave, convex. We won't spend, like I said, just going to mention that this is a possibility. We're going to stick with linear stuff, right? So we're going to try to figure out how can I statistically determine what the line of best fit is, or what is the least squares line. So every actual Y value that you observe in the data set is going to be some function of what the actual relationship is between Y and X. But there's also going to be this epsilon, this Greek letter epsilon, or what we call the error term. Okay? So our error term is going to mean that I can come up with predicted values for Y, but, oh, there we go. My predicted values aren't going to include kind of every single observation's error term. And I think a visual here will help in a second. So really the actual Y values we observe would be what we would predict Y to be, plus some individual specific error, epsilon. So what does this look like visually, right? So let's say I did have this line of best fit. Every value on that line is coming from the equation Y equals A plus B times X. So this is going to give us my predicted Y values. However, just because I see someone, for example, let's say this was like years of education and this was income. For some people, if they've got 14 years of education, I don't know, I would predict their income is, I don't know, just do 50,000 to make it easy. Well, yeah, but there could be the actual person in the data who has 14 years of education and they don't quite make 50,000, right? So our prediction is going to be a little bit off. For this person, there would be an error term that's negative, right? We would predict their income to be 50,000. In fact, it's a little bit less. And for maybe somebody else, maybe they have 14 years of education and their predicted income is a little bit higher, or their error term is positive. So the difference between this line of best fit, this least squares line, and our predicted Y values and the actual Y values in the observation, that's just our error term. Okay. So what we're trying to do is, so we're thinking about here, I've just got another visual similar to kind of what I just drew, but at this X value, I can come up with a predicted Y value from my least squares line or my line of best fit, but the actual observation, the Y value is a little bit different than that, right? So my predicted Y values are on the line. The actual Y values are the scatter plot points. Excuse me. So for this one observation, I've got a positive error term, right? I can come up with a predicted Y, oops, but it's a little bit less than the actual Y value for this specific observation. And then if I had another one, right, where the predicted Y is actually a little bit too high, then the error term for the actual Y value must be negative. Okay. So how can I figure out, right? I've got these lines drawn in there. We're not just going to be doing this by eyeballing it, right? So what we're going to do, how do we find this intercept and this slope value? Or how do I find what the best line of best fit is? How do I find those two values that would give me that line of best fit? So what we're going to do is we're going to try to choose these two values. We're going to try to choose an intercept and a slope that would give us a line that minimizes the sum of the errors that we're making. So remember, if we use this line of best fit, we're making errors. I mean, notice like some of them are close, like this one, but for most of the observations, our predictions are going to be a little bit off, right? So what we're going to try to do is we're going to add up all of the errors that we make. And in fact, similar to the variance, we're not just going to add up the errors, but we're going to add up the squared errors, right? So deviations, like we kind of did for the variance, deviations from the mean squared, it over penalized outliers, same kind of idea here. We're going to over penalize really bad predictions, right? When we have really large error terms. So this is kind of remember, right, when we're adding up the sum of the squared errors, remember the error term. Oh, there's that. There we go. Go back. There we go. The error term, if I just kind of rewrite this a little bit, is going to be the actual y value minus the predicted y value. Okay. So my error term is the actual y value minus the predicted. And we're going to do this for every single observation, square that error, then add them all up. Well, I can rewrite this predicted y value as the function I was using to make those predictions, right? The intercept plus the slope times the actual x value. So what I'm going to do is I have this sum of the squared error term equation, sorry, sum of the errors squared equation. I'm going to try to choose these two values that minimize the sum of those squared errors. So what are we going to do? Take derivatives of this function in respect to both of those things. And then we have two equations, two unknowns with a little bit of work. I think I just reiterated the same slide. Oh, there we go. Sorry, I added in this additional one. So this was a one step. So I'm summing the squared errors here. So I just kind of wrote it out with the additional step in there. Now, there we go. If I solve those two equations, two unknowns, I end up with this is going to be my slope, or what finds me the slope. So I could go through the data, find every single observation, the deviation of x from its mean times the deviation of y from its mean. Notice this looks kind of similar to our covariance. Right? We're then just going to divide by the sum of, well, notice, oh, this is the deviation of the x values from the mean squared. This is kind of similar to the variance in x. So the intercept had an easier equation. Once we calculate what the slope is, the intercept is just the average y minus the slope times the average x. Okay. Now in practice, we're not going to really have to use these formulas because we have these tools like Excel that can do all of this work behind the scenes for us. But I'll kind of show you this is we can use these in Excel as well and reproduce this without making it too boxy. You can also, this is just another, if you rearrange some things, you could do it this way as well. Once again, we won't actually be using this equation by hand. We'll be using Excel to do the work for us. So mostly, the problems you'll see from this chapter, it's not going to be as much computational. It's going to be a little bit more interpreting the results that Excel gives us. So, um, you know, I'll go through how we do this in Excel, like how we find all these different components, like whether I use this version or this version, but the ultimate is going to be we use Excel, right? Now I'll show you this. These are kind of the how you would add it for a PC. So you go to File, Options, Add-ins, select the Analysis Tool Pack, hit Go. It's pretty self-explanatory. If you're having issues, I would also kind of suggest, I don't have a PC to kind of reproduce this in a video, but if you search Data Analysis Tool Pack, add-on Excel, in YouTube, there's probably a million videos, but this should be enough. So on a Mac, I already have it added into mine, but if you go to Tools, Excel add-ins, make sure this analysis tool pack is selected. The step-by-step in the slides is for a PC. It looks very similar. It's going to be called the same thing. Analysis tool pack is one you want to make sure is added and it's added, and then it shows up under the data tab. Okay. So I'll kind of do this by hand first, and then I'll show you the power of this data analysis tab. So if we go back to that formula we had to calculate the slope, let's say I just want to do it between the cases per person. This is my Y variable and the percent vaccinated being my X variable. So I think that, if county has higher percent of their population vaccinated, maybe they didn't see as many cases, right? So the first thing we needed, kind of that numerator, was a sum of the differences between X and X bar, right? Or the mean, Y minus Y bar. So let me pull this back up. Where was it at? I had my PowerPoints. There we go. So here. So the sum of the deviations of X from the mean times the deviations of Y from the mean. So that's what I'm going to do right here. So this one I'm going to say, okay, this is X minus X bar times Y minus Y bar, right? And then I'm going to go through every single observation. I'm going to say, okay, well, actually, what am I going to need to do? I need to put these mean values somewhere. So I'm going to move this over. a little bit, give myself some room. So just going to use the average function to calculate the average of my x variable and average of my y variable. Right, so I've now got those two values. Oh, did I select the same? Okay, they just happen to be kind of similar. So I will take, for every single observation, I'm going to take the x value, which was the percent vaccinated, and subtract the mean. Now, when I copy this down, I want to do, want the observation value to update, but I always want to keep using the mean. So I'm going to put some dollar signs around that. Hit enter. I'm going to do the same thing over here, except for now, I'm going to be taking the y value and subtracting the mean of y. I'm going to put those in there. And then going to drag this down. I didn't set this up next to the data, so this is going to be kind of a pain. Actually, I'll show you how to make this, or make our lives a little bit easier. So when I move these, it's going to update the cell. So let me put this right next to it here. So just to verify, okay, it's still using those means that I calculated. If I have it right next to the data, when I go over to this, see how my cursor becomes a black plus sign. If I double click, it'll do that all the way down to the very end of my data set. Right? It saves me a lot of time dragging it. Right? Same kind of thing here. What am I doing? Okay, I'm going to be taking the deviation from X, deviation from Y, double click. Now I could say, okay, what I want to do is add up all of these products, right? Oops. So enter. Okay. So that is my numerator, right? From every observation, I took the deviation from X times the deviation from Y, and then added them all up. That's what this summation sign means. The next thing I'm going to do is go through every observation, find the deviation from X squared, and add all of those up, right? So X minus X bar squared. So I'll take the X value, which was the percent vaccinated, subtract the mean, right? Once again, freeze that because that's not going anywhere. So here's my deviation from the mean. I then had to square it. I'll hit I'll double click. Well, here, let me go back so I can show you. There we go. I'll double click so that it does it for every single observation. I'll then add all of those up, right? I now have my numerator and my, I don't even know, denominator. There we go. So all I have left to do, right, to find my slope value for B would be to take that numerator divided by my denominator, and I get the slope is about negative 0.25. Okay. I could then say, all right, well, what's the intercept? Well, I said the intercept, if we go back to the slides, take the average y minus the slope times the average x. Okay. So here, what was my average y value? Right here, minus the slope times the average x value. So here's my intercept, here's my slope. Okay. I don't have to do this every single time. This is a lot of work, right? If I have that data analysis, essentially I can go to this regression option. I'm going to say, okay, what's my y variable? I'm going to click this little icon next to it. I'm going to go to oh yeah, cases per person, hold command and shift, control shift on the Mac or control shift on the PC, hit the down arrow, selects the whole range of data. What about my X? Well, this is kind of a pain. Got to scroll all the way back up to the top. Now, if I can remember what column it's in, I can kind of start at the bottom. So I could scroll over to the top and do this, but you've probably seen me do stuff like that. So here, if I just remember that the percent vaccinated is in this column Q, I could select the bottom, hold Control Shift, Command Shift on a Mac, hit the up arrow. Now, while still holding Shift, take my hand off of Control or Command, hit the down arrow. Now I've got, oh, my percent vaccinated selected. Okay. So now I've got my, now I could also type this in if I can kind of look and see what column it's in, different ways of doing it. Now, I didn't select the labels here. I probably should have. So I'll do it once without it and then show you why usually you would want to select the labels. So I won't play around with anything. I'll just hit OK. It creates a whole new worksheet where notice it puts negative 0.25 and 50.79 as my intercept and my slope values. So we'll blow this up so we can see it. Now there's a bunch of other stuff that we'll end up talking about in this output as well. But for now, we're just thinking about we want it to tell us what that coefficient is for the intercept and for our x variable. So I go back to this sheet 2. Those are the exact same values I found here, right? So it just does everything behind the scenes and spits it out at me. Now, it also gives me some other interesting information like test statistics, p-values. We'll eventually start doing some hypothesis testing with this, okay? Now, I'll show you why usually. Go to my data tab, hit regression. It usually stores in what I've done. So instead of starting with that first line of data, I'm just going to go in and I could reselect this, but I know oops. I want to go to, there we go. I want to start at R1 and then I want to start at Q1. Now, if I start at R1 and Q1, I've now selected the labels. So I'll hit labels and hit OK. Well, now this is kind of nice because then in the output, it lets me know, oh yeah, it was an X variable. Like here was the slope. Oh, come on. Here was the slope. Oh my gosh. It's going to drive me insane. View. There we go. It tells me here's my coefficient, but it's the slope coefficient associated with my percent vaccinated. Now, this might seem dumb, like I'm running just one variable, I can remember what it is. Once we get to multiple linear regression, you're going to have multiple variables here. It's a lot easier to kind of keep track of what slope coefficients go with what variable. So you don't have to do it like this, but kind of proving that that formula will work, right? But you can't always just black box it, right? Use that built-in data analysis tool. All right. So I'll show you just some slightly kind of, well, we'll stick with this example, actually, and I'll make a point here. So when we're coming up with these predictions for Y, the actual A and B values, we can't observe those, right? So we're coming up with, so if you think about, we have sample data, our scatter plot that we were using to find our intercept and our slope, that's just sample data. So you can almost think about it like the values that we were getting from Excel there were actually like sample values for our intercept and our slope because we can't observe we don't have the actual population data. So we can put in different values of X. Every observation, we can put in what that observation's value for X was, but we're coming up with these predicted Y values, excuse me, based off of kind of like what we call the sample coefficients, the intercept coefficient and the slope coefficient. Now, how would I generally interpret this? What would the slope mean? Well, it would mean that, let's say I had X being equal to 1, right? So if X was equal to 1, what would my predicted Y value be? Well, just A plus B, right? What if X was 2? Well, now it's going to be A plus 2 times B. So what my slope is telling me is that for every 1 unit increase in X, here, the slope is how much my Y value is going to go up by. Now, I mean, this seems trivial, like that, but when we interpret these results, it has that exact interpretation. Our slope coefficient is the predicted change in Y from our X variable going up by 1 unit. Okay? And then the way we interpret our intercept is when X is equal to 0, all we're left with is the intercept. So we always say the intercept is the predicted value of Y when X is equal to 0. That's how we're going to start interpreting these two coefficient estimates that we see from Excel. or from other programs, which is what I have in the slides, and I'll show you in a second. But if we go back here, we had our intercept and our slope. We could have also used the data analysis tool to find that. So the way we would interpret this slope coefficient, well, what are the units of this variable? It's percent. So it's 1 additional% of the population that's vaccinated, decrease the number of cases per person by 0.25, right? 0.25 people. And then if a county had 0% of its people vaccinated, the number of cases that it could expect per person was what, 50.7. So that's how we would kind of interpret that intercept and that slope coefficient. Well, let me make sure. Yeah. So pull up. There we go. So I'll show you a different example, and we'll kind of get some more practice interpreting this stuff. So I had this data set laying around, had individuals' incomes and the number of days they smoked marijuana each month. Now, you'll notice this is older data. It was younger individuals, so the median, and this isn't, to take this with a grain of salt, but here's the median income. In fact, the median number of days someone used marijuana was 0. I'm guessing there's some definite selection bias that's in this data, but we'll just take it for what it is, 5,000 observations. So this is going to be what the output might look like from other statistical programs. So it's going to have all the same stuff that our Excel output had, but just displayed slightly differently, right? So it's actually kind of nice because it even tells you, oh, here's your coefficient, here was the estimate. We haven't talked about standard errors or the test statistics yet, so we're just focusing here, okay? So we've got an intercept, or what is sometimes called in other programs, or another word for it is the constant, right? The intercept or the constant. So for someone that uses marijuana 0 days, the expected income here is about 32,000. Then for every additional day they use marijuana each month, the predicted income would fall down by about $253. Right? Well, now, once again, take this with a grain of salt. We'll end up kind of saying why a simple regression like this shouldn't be relied on too heavily. But for now, we got to walk before we can run. Okay. So I've got the slope coefficient. The general way we interpret it's a 1 unit increase in our x variable would change the predicted y value by whatever your slope coefficient is. So here, using marijuana 1 more day a month, right, is associated with a expected income decrease or a predicted income decrease of $253. So that's how we would be interpreting these slope coefficients. What about the intercept? I kind of already alluded to this. It's going to be the predicted income for someone who uses marijuana 0 days a month. Okay. So a couple examples of that. I'll kind of end this video here. This is just setting up linear regression. Next video will be going through how we actually do hypothesis testing based off of these results.